In this video, we will study mesh analysis, or also known as loop analysis. This is a powerful method to solve electric circuits. We can calculate the currents and the voltages in the circuits at different points. To explain this method, I will consider a circuit with two loops. For example, we have this circuit with two different loops, and let us consider two different power supplies as well. The one on the left is source 1, so we will call it VS1. This resistor is R1, R2, and R3, and VS2. So let's consider this circuit and solve it using mesh analysis. Now you can see that there are other methods to solve this circuit. One of them would be the superposition principle, which we will study in future. But mesh analysis gives us a method that we can use to solve for these values as well. In this method, we will assume that there are separate loop currents or mesh currents that are flowing in each loop. And then we will get multiple equations. For example, if I have two loops, as I have over here, then I will get two equations that will involve the currents. And then using those two equations and two unknowns, I should be able to solve the actual currents that are flowing in the circuit. So let's get started and see how it will work. So let's assume that in this loop, I have a current IA that is flowing in this loop in a clockwise direction. And in the second loop, I have a different current, which is IB, which is also flowing in a clockwise direction. Now, IA and IB are based on our choice. We can choose clockwise direction or we can choose counterclockwise direction. And this doesn't actually represent the actual current that will flow in the circuit. And we don't really need to know at this point what is the actual current that will flow in the three different resistors. This is our assumptions, and we are free to choose any assumption that we would like. But as a practice, I recommend that you choose one direction and one method of doing this, and then you can stick to that method. This way, you will not make mistakes. So let's say these are the two directions that I chose, and based on that, we will solve the circuits, and then we will find the actual currents in the circuit. So the first thing is to apply KVL to the two different loops, and that will give us two equations. So let's apply KVL. We have discussed KVL in one of our previous lecture, so you can go and see that if you haven't. To apply KVL to, let's say, loop 1. So let me just say loop 1 over here. KVL says that voltage rise should be equal to voltage drop. Now, when I move around this loop, I will have a starting point, let's say A, and from this point, I will go clockwise, and I will see where do I see a voltage rise and where do I see a voltage drop. To be able to apply KVL, we need to first assign the voltages to all the different components in the circuit. In the first loop, we have a voltage source, VS1. This is very simple because a voltage source, the negative terminal, is always at a lower voltage than the positive terminal. So therefore, when I'm going from A to B, for example, this would be a voltage rise for me. However, if you go counterclockwise and you go from B to A, then that's a voltage drop. So you need to just see the circuit and decide if this is a voltage rise or a voltage drop. So for me, this source will be a voltage rise. Now, the other two resistors, the resistor R1 is simpler to decide if it would be a voltage rise or a voltage drop. According to this circuit, the current IA is flowing in the resistor from left to right. So the current in R1 will be actually IA once we solve it. That's the current that will be flowing in R1. Now, if IA, when we solve it, and if it turns out to be positive, then the current will be going from left to right. If IA turns out to be negative, then the current will be actually going from right to left. But based on our assumption of IA is moving from left to right, and the current always go from a higher potential to a lower potential. So therefore, this voltage V1 across resistor R1 will be a voltage drop when I go from point B to point C. It is a voltage drop because I'm going from a higher potential to a lower potential. So that is easy to understand. The main source of confusion that I have seen is R2. Many times we are not sure what to do with R2. So to give myself some space, I will delete this R2 from here and just imagine that this is R2 actually. Now, when I'm in loop number 1 or loop A, in that loop in R2, I have two different currents flowing. So maybe let me draw it here. So this is the resistor R2. According to the directions of the current that I have assumed, I have a current IA that is going downwards in this resistor. And I have a current IB that is going upwards in the same resistor. So we have two different currents flowing in this resistor. Now, how do we assign the voltage to this resistor? We cannot, at this point, we cannot actually know which would be the right direction of the current that will flow because we have not solved the circuit yet. But we know that the current will always flow from a higher voltage to a lower voltage. So if IA is larger than IB, if that's the case, then, for example, if I say IA is 2 ampere and IB is 1 ampere, so then the net current that is flowing in this resistor is actually 1 ampere going downwards, which will mean I need to assign a positive sign here and a negative sign here if IA is larger than IB. All right. So this means the positive would be on top and negative on the bottom. And then when I go from point C to point D in my circuit, this would represent a voltage drop. Okay. On the other hand, if IB is larger than IA, then the net current will be flowing in the upward direction. And if the net current is flowing in the upward direction, then this point should be positive and this point should be negative. And in that case, it will represent a voltage rise for me in loop number 1. So at this point, we do not know if IA would be larger or IB would be larger. So now what we will assume is that when I'm in loop 1, IA is larger, all right? And when I'm in loop 2, when I'm solving loop 2, then IB is larger. I will assume this, and then we will solve the circuit. But again, this is not important. You can have any assumption. As long as you assign the voltage polarities and the current directions correctly, you will always get the same result. So let me explain how we will do this. When I am in loop A, I will assume that IA is larger than IB. With that assumption, the current is actually flowing downward. So I will assign a positive here and a negative here, and this will be my voltage V2. And you can see now when I'm applying KVL in loop A, let me call it loop A because I called it IA, so loop A. So when I'm applying KVL in loop A, I have decided to move clockwise. And then when I go from point C to point D, I see that this is V2 is a voltage drop. All right, because I'm going from a higher voltage to a lower voltage. So that's a voltage drop. So now let's apply KVL to this. Going from point A to point B, I have a voltage rise of Vs1. So Vs1 is a voltage rise for me. Then going from B to C, I have a voltage drop, which is V1. And then going from C to D, I have another voltage drop of V2. So KVL gives me this equation, which says voltage rise, Vs1 is equal to voltage drop of V1 plus V2. V2 is a voltage drop because I have assumed IA to be larger than IB. Okay, now let's see what the next step we can do here. Vs1 is equal to V1. Now V1, according to Ohm's law, is the current in resistor 1 multiplied by the resistor 1 value. So that is IA times R1 plus V2. Now V2 is actually a voltage which is the product of the current in R2 multiplied by R2. The current in R2 is made of two parts, which is IA and IB. IA is going downwards, IB is going upwards. So the net current in the resistor R2 is IA minus IB. Okay, this is the net current multiplied by R2 will give me the voltage. Now you see I have chosen IA minus IB. I did not choose IB minus IA because I have assumed that in this loop IA is larger. So with this subtraction IA minus IB, I will get a number, a current, which will be positive. And that positive value multiplied by R2. So positive will mean here that the current in R2 is actually going downwards. Okay, so this subtraction actually makes the whole difference, and this causes the problems most of the time. Mistakes are made with this assignment. So because I have assumed that the polarity of the voltage V2 is such that it is higher voltage on top and lower voltage on the bottom, so which means the current is actually going downwards. And if the current is going downward, I have to assume that IA was larger than IB. So therefore I have to use this subtraction, IA minus IB times R2. That will give me the voltage correctly across R2. And it is a voltage drop. So therefore I have written it on the right hand side of this equation. All right, so that's okay, I believe, for now. So let's see. We have this equation now, and we want to simplify it a little bit. So we have Vs1 equals to IA times R1 plus IA times R2 minus IB times R2. And one more step would be Vs1 equals to R1 plus R2 multiplied by IA minus R2 times IB. Now this is the standard form in which we want to write our equations. And the form is that we have one unknown, we do not know IA, and we have another unknown. So we have two unknowns in this equation, and the rest of the quantities are known to us because we know the value of the resistors and we know the voltage source. So this is our one equation that we will use later on to solve IA and IB. All right, so far so good. Now let's see how will we go about loop B. So we will apply the same process and we will say KVL in loop B. To apply KVL in loop B, we know the statement of KVL, which says voltage rise is equal to voltage drop. Okay, so now let's see which one is voltage rise and which one is voltage drop. Again, I will stick to my plan that I always do so that I feel comfortable and I don't make unnecessary mistakes. When I'm applying KVL to loop B, I will move in the clockwise direction as we did in loop A. So to move in the clockwise direction, I will need to find out what will be the voltage across R2, the voltage across R3, and the source voltage Vs2. So now when I'm in loop B, I will assume that IB is larger than IA. Okay. So if I assume that IB is larger than IA, then the net current is actually flowing upwards in this resistor. Okay, so the current is flowing upwards in this resistor. It is not necessary for me to do that. We will show you if I don't assume that, I will still get the same result as long as I'm consistent. So now, for now, let's assume IB is larger than IA, which means the net current is flowing upwards. If the current is flowing upwards, then this means that this should be the positive terminal and this should be the negative one, because the current is going upwards and the current always moves from higher voltage to lower voltage. So in this loop, my V2 polarity will be opposite to the one that I have chosen in loop A. That's one thing. The second thing is that IB is now flowing in R3 and it is just flowing from left to right. So therefore V3, this is V3, that will be the polarity of V3. And then this is the positive terminal of the source and the negative terminal of the source. So let's do the following. We will apply KVL. We will go from D to C, and then from C to E, and then from E back to D, or we can call it F. F and D are at the same voltage as well as A, so it's not actually a different point. All of these 3 points have the same voltage because the copper wires, there is no voltage drop across the copper wires. So let's apply KVL. And according to the KVL, going from D to C, it's a voltage drop, right? It's a drop. Then going from C to E, it's another voltage drop. And then going from E to F, that's another voltage drop. So I have all three voltage drops and there is no voltage rise. So let's apply the KVL then. So the KVL will say that there is no voltage rise, and the voltage drop, the first one, was V2, because we were going from point D to C, so that is V2, the amount of drop is V2. Then we have a next drop of V3, and then we have a next drop of source voltage, so this second source voltage. So this is my equation. Now let's solve this equation a little bit. So I can say, if I want to keep the constant on the left hand side, for instance, so I will say negative Vs2 equals to V2 plus V3, which means negative Vs2 equals to V2. So now what is V2? The voltage V2. The voltage V2, according to this assumptions that IB is larger than IA, and it is a voltage drop with a higher voltage on the bottom and lower voltage on the top. So this is a drop if IB is larger than IA. Okay, so this is a drop if IB is larger than IA. So therefore, V2 is IB minus IA times R2. Okay, so now you see the difference. In loop 1, it was a voltage drop for me using IA minus IB because I assumed IA was larger. Now in loop 2, it is a voltage drop for me because I assumed that IB is larger than IA. Okay, so therefore I'm going to write IB minus IA, and it will be a drop. All right, so with that, because if you see, if IB is larger, then this difference will be a positive quantity. And if it's a positive quantity, it will give me a positive V2, and positive V2 in loop B is defined in this direction. Okay, so that's V2. And V3, of course, is IB times R3. All right, so now let's simplify this. Negative Vs2 equals to negative R2 times IA, and then positive R2 plus R3 times IB. This is the final equation, but I see two negative signs and one positive. We like more positive signs, so let's multiply both sides with -1. So I will get Vs2 equals to R2 IA plus R2 plus R3 IB. I have made an error here. The IB term should be negative instead of positive. This error has been fixed later on in the video. This is my final equation, and you can see that we have written it in the standard form, where I have the two unknowns, IA and IB, and the other quantities are known. I will call this my equation number 2 that we will solve and find IA and IB. All right, now I understand that this business of choosing which current is larger than which current can be confusing sometimes. So before we move on to solve these two equations, what I want to do now is to show you that we do not need to make that assumption. Okay, we can just make one assumption for both the two loops, but then we solve it based on that assumption alone. If I assume that IA is larger than IB, so I will keep that assumption for both of the loops. Okay, and then you will see what will be the difference. In the end, the two equations will come out to be exactly the same. So let's quickly do this again. I have a voltage source, one resistor, another resistor, another source. This is R1, this is R3, R2, Vs1, Vs2. I'm having a loop current here, IA, and I have a loop current here, IB. At this point, we do not know which current is larger, but we can make an assumption, and then we will use the same assumption for both of the loops. Let me assume IA is larger than IB. Okay, so this is our assumption, and we will use this for both of the loops. In loop A, the current in R1 is flowing from left to right, so this is the voltage polarity, and the voltage is V1. In the resistor R2, remember the current IA is larger than IB's. IA is going down, IB is going up, but the current going downward is larger than the current going upward, so the net current is going downward. Therefore, this is positive and this is negative, and we're going to call it V2. When I am in loop B, again, I'm going to use the same assumption. IA is larger than IB. With that assumption, this must be positive, this must be negative, and this would be my voltage V2. V3 is easy because IB is just flowing, because there is only one current, IB, flowing in this resistor, which is going from left to right. So this is positive and this is negative, and the voltage drop is V3. So now we have assigned all three voltages in the two loops, and let's apply KVL to loop 1. So KVL to loop A, we know that voltage rise is equal to voltage drop. I'm going to start from this point A, and I will move clockwise. I see a voltage rise of VS1, and then I see a voltage drop of V1, and I see a voltage drop of V2 in this loop. And that's in this loop, we have only these three voltages. So that's the KVL for loop A. Now let's say VS1 is equal to V1, which is IA times R1, and V2 is IA minus IB times R2. So I have chosen IA minus IB because this will give me a positive number. Okay, this will give me actually the current that is flowing downwards, correct? Because IA is larger, so that is the current going downwards. And if the current is going downwards, so then this is the correct voltage polarity. And when I move in this loop clockwise, I'm actually going from, let's say, this point C to point D. Then this is a voltage drop. So therefore, I have written it on the right-hand side of my equation, where I'm writing all the voltage drops. So far, we have the same equation as equation 1, because for loop 1, we had the same assumption before. So VS1 is now IA times R1 plus R2, and minus IB times R2. And this is the same equation as we have above. So this is my equation 1 as before. Now let's look at loop 2, KVL in loop B. In loop B, I have to apply KVL. And now if I go from clockwise direction from point D to C, then C to E, and then E to F, I will move in this direction, and I will see what is a voltage drop and what is a voltage rise. So the first voltage, when I go from D to C, now this voltage is a voltage rise for me. Okay, so you see the difference from before. Now we are assuming that IA is larger than IB. So if that's the case, then this is a voltage rise for me when I go from D to C. So therefore, V2 is a rise, V3 is a drop. When I go from C to E, this is a drop. And then when I go from E to F, I have another drop. All right, so let's apply KVL. Rise is equal to drop. Rise is V2, and drop is V3 plus VS2. Okay, so that's our KVL. Now, a potential problem can occur here. How will you write V2 using Ohm's law? Ohm's law will tell you that the voltage is equal to the product of the current and the resistance. So the current in resistor R2, when I'm in loop B, we know that now the current has to go from top to bottom, because you see we have higher voltage on the top. So the current has to go from top to bottom. And this means IA will be larger than IB. Okay, so the net current is actually flowing in the direction of IA, because IB is smaller than IA. So now V2 should be written in this way, that this is actually equal to IA minus IB times R2. So you see the difference here again. We have to now change the signs of the two currents over here. Because IA is larger, so this difference will be a positive quantity and a positive current quantity, which means the current is actually going downwards. If the current is going downwards, therefore the correct voltage polarity would be this, as we can see, and therefore this is a voltage rise, so therefore it will be written on the left side of the equation. V3 is simple as before. It is IB times R3 and then VS2. So you see, two things happened. One, I had to change the sign of the two currents, IA minus B, IB, or previously it was IB minus IA. Secondly, previously this quantity was on the right-hand side of the equation, right? So in effect, what happened is that we got opposite signs, negative signs, two times, right? First, this quantity was on the right-hand side, and second, we had to flip the signs of IA and IB, the difference. So having two negative operations means having no operation at all, right? So therefore, this is the same equation as before. If I say now, for example, that I want to write this equation in the similar way as I wrote it before, so therefore I will have, so let's do the following. IA times R2 minus IB times R2 equals to IB times R3 plus VS2. So I will bring VS2 to the left-hand side and the rest of the quantities to the right-hand side. So I will have negative VS2 equals to negative IA times R2, positive IB times R2, positive IB times R3. That will give me negative VS2 minus IA times R2 plus IB times R2 plus R3. And this is my second equation using mesh analysis, but choosing to have the same assumption that IA is larger than IB. And now you compare this second equation, this equation VS2, compare it with the one that we got earlier, this one. Sorry, I have a negative VS2 here. So no, I made it positive, positive, and then this one should be negative, because I multiplied by -1 everywhere. So we have this equation over here, which is exactly the same over here if I multiply it by a -1 on both sides. So I will have this equation. So now you can see that either method or either option will work the same. You will get two equations that are exactly the same. However, it is up to you. It's your choice which method you feel to be more comfortable with. I like the first one because then I just assume that in every loop, whichever loop I am, I will choose that that current is the largest current. And I actually don't need to remember what was my original assumption. I will always just say if I'm in loop 3 is the larger current, and I'm loop 1 is the larger current, and so on. All right, so that can work for you. Or if you don't like that method, because you see the problem with that method is that V2 gets opposite polarity in both the loops. So if you do not like this to happen, then you can choose this method that you say, okay, let's fix the direction of V2 and apply the two currents and then solve KVLs. Now the next task is to find the two currents. I'm sure you might have done this before when you have two equations. For example, these are my two equations. If you have two equations and two unknowns, then you can easily solve it. We can get the value of one unknown from one equation and put it in the other equation, and that will allow us to find both IA and IB. So let's assign some numbers to simplify these equations, and then we can see how to solve them, and this will also enable us to visualize what is actually happening. So let's say for the same circuit, I will choose that VS1 is 5 volts. So I have a 5 volt battery or a voltage source, and VS2 is 3 volts. So I have two different voltages, and I chose two different voltages because I want to show that one of the voltage may be producing the current and the other one actually is less in voltage and the current may be actually charging that battery. So these are our two voltages. For resistors, for the calculations to be simple, I'm going to assume that R1 is equal to 1 ohm, R2 is equal to 2 ohms, and R3 is equal to 3 ohms. So this will just help me remember easily. So now let's put these numbers into our equations. The first equation is that Vs1 equals to IA times R1 plus R2. So I will say that 5 is equal to IA times R1 plus R2, which is 1 plus 2, so that's 3. And the remaining part was negative IB times R2. So it will be negative IB times R2, which is 2 ohms. So therefore, my equation is now very simple. I have 3IA minus 2IB equals to 5. So I get this equation now. And let me just call it equation 3. So I got this equation from equation number 1. Right, so R1 is 1, R2 is 2, so 1 plus 2 is 3, and R2 is 2, so and Vs1 is 5. So that gives me the first equation. For the second equation, I have Vs2, which is equal to 3 volts, and IA times R2, which is 2, negative IB times R2 plus R3, so that is 2 plus 3, which is 5. So I can write this equation now as 2IA minus 5IB equals to 3. So that is my equation 4. Okay, so now it would be much easier to apply that method that we have two equations and two unknowns. These are our two equations, and our two unknowns are IA and IB. So let's consider equation 3. So from equation 3, I will get the following, that IA is equal to 2IB plus 5 divided by 3, right? You can see from equation 3, you will get IA equals to this much. Now we have a value of IA in terms of IB. So now if I put this value in equation 4, so if I put this value of IA in equation 4, then you will see that IA will disappear from equation 4. So I will get 2 times IA, so that is 2IB plus 5 divided by 3. So I put the value of IA in this equation over here in 4. So I have 2IA minus 5IB equals 3. All right. Now, you see in this equation, we don't see IA anymore. And now we have just an equation in which IB is the only unknown. So all we need to do is now to just find this IB from this equation. All right, so the first thing that I can do to get rid of this 3 in the denominator, that I will multiply by 3 on both sides. So if I do this, I will get 2 times 2IB plus 5 minus 15IB equals to 9. So I just multiplied both sides by 3. Second, I will multiply this 2 inside the parenthesis, so I will get 4IB plus 10 minus 15IB equals 9. Now I have negative 15IB and 4IB. So when you add both of them, we will get negative 11IB. And I have this 10 on the right hand side, so I will take it to the left hand side, sorry, from the left to the right, and it will become negative 10, so I will have negative 1. And now you can see that this negative and negative can cancel out. IB is equal to 1 over 11. So we found the value of IB. 1 over 11 is equal to 0.091 ampere. So this much current will be flowing. This is the current value of current IB. I can also write it as 91 milliampere. Okay, so that's my IB. Now we got IB. Let's put the value of IB from here into here to find IA. So therefore IA will be 2IB plus 5 divided by 3. So IA is equal to 2IB plus 5 divided by 3. I will have 2 times 0.091 plus 5 divided by 3. And if you just multiply them, add 5 divided by 3, IA comes out to be 1.726 amperes. So IA is much larger, 1.726. So we got our two currents. Now we can actually say what will happen in the circuit. So we got the two currents, 0.091 and 1.726 amperes. Now, let me show one more time here how much current will be flowing in each path or each component. VS2, VS1. So this was, for us, this was 5 volt and this was 3 volt. Okay, R1, which is 1 ohm, R2 was 2 ohm, and R3 was 3 ohm. Okay, we had here we had a loop current. We assumed IA flowing in this direction and a loop current IB flowing in this direction. Okay, so now what is the current in R1 over here? You can see that the current in R1 is equal to IA. Okay, so the current in R1, so I'm just going to call it I1, is equal to IA. So therefore this is 1.726 amperes. So this much current flows in this resistor I1. Let me call this one I1. I1 is the same as IA. And if this current flows in a resistor of 1 ohm, how much will be the voltage drop across this resistor R1? So the voltage drop V1 will be I1 times R1, which is 1.726 multiplied by R1, which is 1 ohm. So that is 1.726 volts V1. So the voltage drop across this resistor is 1.726. That's the voltage drop. I can write it over here, 1.726. Okay. The next current that we can find easily is the current I3. So the current I3 over here is the same current as IB. Okay, so we can say that I3 is equal to IB, which is 0.09, let's say 0.09 amperes. If this is the current I3, which is flowing in this direction of the IB, then the voltage drop across this resistor would be V3, which will be I3 times R3, which will be 0.09 times 3, and V3 is equal to 0.27 volts. So this much voltage, 0.27 volts, will drop across R3. So I will have a positive here and a negative here, and this would be 0.27. Okay. And the last part is the current in resistor R2, and that is initially we didn't know the actual current direction, but now we have found that IA is larger. As you can see, IA is larger than IB, so therefore the actual current is flowing downwards. So the current in R2 is actually flowing downwards, and this is I2, and the value of I2 is IA minus IB, because IA is going downwards. So the larger current, so the net current is going downwards. So therefore we have to choose IA minus IB, so that I2 can be flowing in the direction of IA. So therefore I2 is IA minus IB, and that will be 1.635. So this is I2. If this is the value of I2, then the voltage drop across R2 will be I2 times R2, which is 1.635 times 2, and V2 will be 3.27. So that will be our V2, 3.27. So let me write it here. I have 3.27. Okay, so we have found all the values in the circuit, and now you can take a look and see if everything makes sense. First of all, the 5-volt supply is actually producing current. You see the current I1 is coming out of this supply. On the other hand, the 3-volt supply is not producing a current. Actually, it is receiving current, and that current is the same as I3, and this battery is being charged. Finally, the voltages are shown on the diagram. So you can see that KVL should be satisfied. So for example, if I go from point A, so I see a 5-volt rise, and then I should see from point B to C I have 1.7, and then C to D I have 3.2. So 3.2 and 1.7, if I add these numbers with significant digits properly, then this drop will be equal to 5-volt. So 5-volt rise will be equal to 5-volt drop. Similarly, in the second loop, my rise is actually this one. This is my rise. So I'm going from D to C. So I have a 3.27 volt rise, and then I have 3 drop and 0.27 rise, and you see that KVL is satisfied. So all the laws are satisfied. This is the final solution. I hope you enjoyed this video, and if you did, please subscribe my channel. And that's it for today. I'll see you guys next time. Bye for now.